Hey, we're looking at Calculus, Chapter 5. Chapter 5 is entitled Integration. So now we're moving on to the next phase in our calculus journey. So we start off in section 5 when we talk about approximating area under curves. Okay, so we were given a function f of x at some point. And then we started looking at, well, let's take the derivative of this function. If we take the derivative of this function, that tells us the slope of any tangent line. It told us that kind of that instantaneous values on how things are moving. And then we applied then our second derivative just to see more curvatures, everything else. So we had our derivative part. Now we're going to start taking a look at the integral of what our function is, or basically what was also known as the antiderivative. Okay, the antiderivative, we have the derivative go backwards on it. Here we have our function. Now we're going to apply the integral to it, but yet it's still working with the same features. Well, we're trying to figure out, well, what is this really telling us? Okay, so spoiler alert, it tells us the area under a curve. Okay, so there are different ways we start working with this, different ways we have to work or see how things go, why it works, theorems as it works. So as we start off, we kind of start looking at what is the geometric meaning. Okay, so area under a velocity curve. Once again, we kind of recall back here. It says if the velocity of an object is positive, its displacement equals the distance traveled. Okay, so displacement equals your rate times time. So then we start looking at the values. Once again, we have our velocity function, and then we would talk about the area as the displacement in here would tell us the distance. Once again, if we have the time and the velocity, multiplying these two together, or if we notice it's a rectangle, length times width, we get that overall value that's in here. But that's nice, that works great, but is everything a nice constant velocity? No, there are certain times that we're going to have functions where they're not going to follow these nice straight lines. There's going to be some curvature going on in here. So what we're going to have to start doing is we're going to have to start approximating what's going on. And what we start looking at is we start looking at drawing these rectangles where in this case we take the midpoint as the height of this rectangle. And then, so this is 4 units wide. Now here we break it 2 units. Now here 1 unit. And as you see, we have area that isn't, but hopefully that area is going to kind of make up for this right here. But as we get more and more precise with these rectangles, we see we get a better curvature fitting. And then we kind of come down here and they talk about, well, here we got 64 rectangles that are under here with our widths and everything. And then we're going to start adding all these individually as we go through. So one of the main things on this is it kind of starts talking about Riemann sums. Okay, so approximating areas by Riemann sums. Okay, so if we consider what's happening on here, we start looking at the simple fact that our delta x equals b minus a divided by n. So once again, we want to try to figure out our change in our x, and we want that to be constant, okay? So if we look right here, we don't want to have a rectangle here, then all of a sudden a big rectangle, then a smaller one, then a big... No, we want to be constant and have equal rectangles in here. Main purpose is because if we can have that main rectangle within here, we can look at this regular partition rule. Okay, so in this regular partition rule, they kind of talk about the equal lengths here, and then our endpoints, and then once again, we're just going to have to find what our y is. So we look right here, this is basically what it's saying. It's taking the height times the base. We're going to take f of whatever x value we have times our delta x. Okay, once again, where k is kind of talking 1, 2, 3, wherever we talk about it. Now, summing the areas in the rectangle, so we start looking at this, that although the idea of integration was developed in the 17th century, it's almost 200 years later when Riemann really started putting this into work in theory and had that underlying value of what this integration is going to lead up to. So let's look at Riemann sum. Riemann sum talks about suppose f is defined on a closed interval from a to b, which is divided into n subintervals. Once again, each by a delta x in length. If x sub k asterisk here is any point in the kth subinterval, for instance, k1, 2, 3, 4, so on, all the way up to n. We talk about the summation of this, where we have our first one, our second one, our third, fourth, all the way to the nth one, each having a width of delta x. Now, this is called the Riemann sum. Okay? Now, there are three types of Riemann sums. There is a left Riemann sum, a right Riemann sum, and a midpoint Riemann sum. Okay? So, looking down here, how to tell the difference. Basically, in the left Riemann sum, we use the height of every rectangle underneath is based off of the left-hand side for the value. Okay, so the height comes here. On the right Riemann sum, we use the right side. So we see it's a little different. Once again, the left side right here, the right side is a little bit lower, but now where this was below, this now is above. So we start seeing a little difference in these values here. And then the midpoint talks about, well, if we start here, and then our delta x, delta x, delta x, we go in the middle of this, and we plug that value in for that height in here. And basically, this just adds together. So we find the area of all these separate ones, and we add them together. And this gives us an approximation for the area under the curve. Now, once again, they're looking at a sine curve here. This is kind of that curvature that they're relating to. And we're talking that area underneath. Now, once again, this area talks down to the x-axis or down to a value down here. That kind of changes as we go throughout problems. One of the main things that we really start talking about on here with Riemann sums is we start talking about that we're taking a summation. Okay, so we're summing, we're adding these up. So we can start using some of our sigma notations. And there's some very common sigma notations that we have in here. So we have this table down here that relates to our summations. We talk about that if we just have a constant line, we're just going to take however many intervals we have and multiply by that constant. That's what it is. If we have a linear, okay, just that basic linear, we're going to take the number of intervals times the number of intervals plus 1 and divide it by 2, and that's going to give us that summation of that part. K squared and k cubed. Once again, we got some values in here. So these are some common ones. If you remember back in college algebra, when you were in my college algebra class, we went through and we proved these and that they actually work for all these values. So it's one of the reasons why we talk about this. So once again, using Riemann sum now, using sigma notation. Okay, once again, if we notice, we had our function height times our width plus our next function height times our width plus so on and so forth here. So we talk about the summation of our function heights times our delta x. Okay. Now, if we come down into this table and talk about the definition of our Riemann sum, left, right, midpoint, once again in here, basically it changes just a little bit in the simple fact that we're talking the summation of our function times delta x. Okay, so in these three cases, the left hand we can look at a plus k minus 1 times delta x. Here we look at a plus k times delta x, and then here that midpoint we talk about minus 1/2 in here. So this is just how we can kind of simplify up these problems a little bit as we go through. Now do realize a lot of this is going to be just brute force. We're going to be working with these problems a little bit more consecutively and not necessarily relying heavily on formulas as we go through. There might be a lot of times we might just finding our values, plugging it in, typing it in, and working out our problems as we go through.